The floor of the Pacific Ocean moved at 4:35 in the morning. While the population along the Oregon coast was still asleep, a rigid block of the Earth's crust shifted approximately 218 kilometers west of the small town of Bandon, at a depth of roughly 10 kilometers beneath the water's surface. In terms of global planetary energetics, the event was logged as a middling magnitude 5.5 earthquake, a metric usually destined for a single sentence in a routine geological catalog. Yet the seismic waves from this specific displacement traveled efficiently through the cold, rigid crust, crossing an international border to be felt as a slow roll more than 300 kilometers away in Victoria, British Columbia. This geographic reach immediately shatters the superficial insignificance of the number. The United States Geological Survey initially registered the event at magnitude 5.4 before refining the data upward to 5.5, a standard calibration that underscores a critical analytical principle in geophysics. The raw magnitude is a misleading indicator of systemic hazard. The primary variable is not the size of the rupture, but its precise address. This moderate energy release occurred on the southern edge of the single most dangerous fault system in North America, the Cascadia subduction zone. It struck precisely 326 years into a seismic silence that began on January 26, 1700, an interval that represents a continuous multi-century loading cycle with a definitive physical limit. The automated warning infrastructure immediately registered the sensitivity of this location. Approximately 4 minutes after the shaking, a brief, automated tsunami warning entry flickered near 43.5 degrees north latitude within the raw monitoring feed before being stood down by human analysts. While the National Weather Service confirmed there was no immediate tsunami threat because horizontal side-slipping transform faults do not displace the vertical water column, this institutional flinch reveals a deep systemic unease. The true scale of this crisis, however, is anchored not in the single morning jolt, but in a profound systemic deficit that accumulated during the days preceding it. In the week leading up to the June 29, 2026 earthquake, the southern end of the Cascadia subduction zone experienced a massive silent surge of tectonic tremor and slow slip, a phenomenon known as episodic tremor and slip. Sensitive satellite positioning instruments and deep seismic networks logged a total of 3,127 separate, ultra-low frequency epicenters concentrated underground beneath the southern Oregon and northern California margins. In a single evening's tally, observers recorded over 500 individual slow-slip events. This means that while the surface appeared stable, the deeper, hotter zones of the plate interface were actively creeping forward, transferring an immense load of elastic strain upward onto the locked, brittle section of the megathrust fault above it. The magnitude 5.5 transform fault earthquake was merely the loud manifestation of a system already wound to a critical threshold. The fundamental mechanical question remains unresolved. Did this silent 3,000 event stress transfer directly trigger the felt earthquake at the doorstep of the locked zone? And is this sequence a routine background adjustment of a busy plate margin, or the final localized failure that precedes a full-scale structural collapse? The persistent reliance on a single magnitude number to evaluate seismic hazard creates a profound conceptual distortion. When the public hears the metric 5.5, the brain instinctively categorizes the event alongside thousands of identical readings that rattle dishes globally without consequence. In the architecture of geophysical systems, however, magnitude is merely one of 3 variables dictating risk, and in this instance, it is the least informative. The true danger is defined by the rigid constraints of geometry and location. To understand why a moderate rupture can paralyze a monitoring network with unease, the logarithmic nature of seismic energy must be fully quantified. Each whole step on the magnitude scale represents an approximate 32-fold increase in radiated energy. A magnitude 6.5 release is 32 times more powerful than the Bandon event. A 7.5 represents a 1,000-fold increase. The megathrust system sitting directly adjacent to this rupture is capable of a magnitude 9.0. An event that releases hundreds of thousands of times more energy than the morning quake. The magnitude 5.5 event was not a massive release. It was a localized failure on a sideways sliding transform boundary, a horizontal grinding of hands that cannot lift the ocean. But this minor failure occurred directly at the threshold of the most heavily loaded structural interface on the North American continent, the Cascadia subduction zone. Here, the oceanic Juan de Fuca and Gorda plates are forced eastward and downward beneath the North American plate at a continuous rate of 30 to 45 millimeters per year, a velocity matching the growth of a human fingernail, yet unyielding in its cumulative mass. Because the shallow boundary is completely locked, this steady convergence has converted 32 decades of plate motion into an immense reservoir of stored elastic strain. The superficial interpretation that this morning's event acted as a safety valve, draining stress from the region, collapses under basic energy budget analysis. The horizontal slip did not alter the vertical loading of the megathrust. The 40 feet of accumulated plate displacement remain entirely intact, waiting to be discharged through an upward thrusting lurch that will violently displace the overlying column of seawater. This mechanical proximity exposes the true meaning of the system's address. It is the physics of a small pistol shot fired inside a room lined with volatile explosives. The minor release of energy did not mitigate the danger. It acted as a mechanical probe along the perimeter of a silent giant. This structural tension directly conditions the human and technological response across the Pacific Northwest. In Victoria, British Columbia, the transmission of low-frequency waves through the rigid crust rocked a population trained to interpret the long, slow roll not as an isolated curiosity, but as a potential herald. This collective reflex is mirrored by the automated warning infrastructure, where the rapid generation and human cancellation of a tsunami warning within 4 minutes demonstrates an institutional flinch. The system treats every moderate offshore event as guilty of being a megathrust rupture until proven innocent, a rational overreaction built on the knowledge that when the locked interface finally fails, the luxury of reaction time will cease to exist. By shifting the analytical focus from the deceptive simplicity of the magnitude number to the precise structural mechanics of the fault junction, the morning quake ceases to be a routine statistical entry. It emerges as a legible acoustic signal, a whisper generated by a minor component of a vast, highly stressed machine that is fully capable of a scream. The deepest layers of this geophysical crisis are entirely silent, existing far below the threshold of human perception. While the felt earthquake registered on the regional consciousness, the true mechanical driver of the system all week was an energetic surge that no human sensory system is built to detect. This hidden process is episodic tremor and slip, an underground phenomenon where vast sections of the plate interface move past each other over days or weeks rather than seconds. In the 7 days preceding the morning earthquake, the deep subduction interface beneath southern Oregon and northern California was vibrating with a low-frequency rumble, generating 3,127 separate, microscopic epicenters. In a single evening, over 500 individual slow-slip events were tallied by regional monitoring networks. This was the quiet part of the sequence, an invisible tectonic migration occurring at depths of 30 to 40 kilometers beneath the crust. At these extreme depths, high temperatures and intense fluid pressures alter the behavior of the fault zone. Instead of locking and snapping like the cold, brittle rock near the surface, the deep fault oozes, creeping forward and releasing its energy too slowly to generate traditional destructive seismic waves. However, this deep relaxation does not alleviate the structural load on the continent. Because the deep creeping section is physically continuous with the shallow locked seam above it, every millimeter of downward slippage acts as a mechanical lever. As the lower plate boundary slides forward, it transfers its stress directly upward, packing incremental energy into the brittle, stuck interface that has been storing strain for centuries. Each slow slip event effectively gives the locked fault a minute, unyielding squeeze. This physical reality deconstructs the common superficial comfort that slow slip events are entirely harmless because they occur regularly on a 14-month cycle. While it is scientifically accurate that hundreds of these episodes have passed without triggering a catastrophic failure over the last 25 years, it is a dangerous misinterpretation to assume the process carries zero risk. The system operates on a statistical progression of accumulating load. The fact that past stress transfers did not cause a major rupture does not guarantee the safety of the current cycle, any more than a history of safe trigger pulls guarantees a gun is empty. During an active episode of tremor and slip, the shallow locked interface enters a state of heightened physical tension, causing a brief but distinct elevation in the probability of a major failure. The spatial and temporal convergence of this specific tremor surge with the subsequent magnitude 5.5 earthquake is what alarms the processing networks. The thousands of silent movements actually displaced more total mass and transferred more cumulative stress into the system than the single felt earthquake that captured public attention. This hidden energy budget exposes a profound systemic irony. The human population reacts exclusively to the noise of a singular moderate rupture, while the planet performs its most significant structural loading in complete and undetectable silence. This modern realization is a direct product of a technological paradigm shift. Before the early years of the 21st century, this entire slow slip surge would have been completely invisible to science. The development of dense, highly sensitive satellite positioning networks planted along the coast allowed researchers to observe the land surface defying its normal trajectory, briefly reversing direction and sliding seaward for weeks at a time. Coupled with the detection of low-frequency tremor signatures on advanced seismometers, science gained the ability to see the deep loading process in near real time. The morning earthquake cannot be understood as an isolated event in a calm system. It struck a margin that had just spent a week being tightly wound by a multi-thousand event subterranean surge, forcing analysts to confront the true state of a system operating near its physical limits. The structural integrity of the Pacific Northwest is governed by an unyielding mechanical clock that has been ticking for precisely 326 years. In the framework of geophysics, the prolonged absence of a major earthquake is not an indication of stability. Stillness on a subduction zone is a direct metric of continuous elastic accumulation. The tectonic plates beneath the ocean do not pause or accommodate human timescales. They continue their relentless eastward descent at a velocity of 30 to 45 millimeters per year. Because the massive interface where the plates meet is locked solid, this constant motion is entirely converted into structural deformation. The edge of the North American continent is being compressed, squeezed, and dragged downward, storing 3 centuries of unmitigated plate displacement within the rock. Simple mathematical tracking reveals the scale of this physical deficit. Since the last major rupture on January 26, 1700, the plates have driven 10 to 13 meters of continuous displacement into a locked seam that has refused to budge. This represents nearly 40 feet of stored elastic strain waiting to overcome the frictional limits of the fault interface. The mechanics of this process can be measured directly on the surface. Highly precise satellite positioning networks installed along the Oregon coast document that the land is not static. It is actively rising and tilting landward. Near the coastal town of Brookings, this vertical uplift has been logged on the order of tens of millimeters over recent years, providing the definitive physical fingerprint of a coast being mechanically spring-loaded. When this system ultimately fails, this multi-century uplift will instantaneously reverse, causing the coastline to drop by a meter or more and allowing the ocean to surge inland. This structural reality exposes the precise threat profile of the southern Cascadia segment, the exact zone where the morning's magnitude 5.5 earthquake and the 3,000 silent tremors occurred. The geological record indicates that Cascadia does not operate as a uniform system. While the entire 1,000-kilometer fault can release simultaneously in a colossal magnitude 9.0 event, the southern segment behaves with a much faster, more volatile rhythm. It ruptures independently and far more frequently than the northern sections. This historical behavior underpins the split probabilities calculated by regional hazard agencies, while the long-term chance of a full margin magnitude 9.0 earthquake sits at roughly 10% over a 50-year window. The probability of a major rupture isolating the southern segment rises sharply to nearly 1 in 3, or 37 to 42%. This means the morning earthquake and the preceding slow-slip surge materialized on the most unstable, highly stressed sector of the entire fault zone. To maintain absolute scientific rigor, this high probability must be isolated from superficial alarmism. A 1 in 3 chance over a 50-year timeline translates to a minute, weekly, or monthly probability. The morning's magnitude 5.5 event does not instantly alter these long-term baseline statistics, nor does a transient slow-slip surge guarantee an immediate collapse. The critical insight is that the system has entered a verified window of statistical recurrence. The average return interval for full margin ruptures ranges between 240 and 500 years, but the fault does not operate on a predictable metronome. Past intervals have been shorter than 2 centuries, proving that the fault does not owe the continent a predictable schedule. The morning's minor transform fault rupture was completely incapable of draining this immense energy reservoir. Its magnitude 5.5 release left the 40 feet of accumulated plate displacement entirely untouched. The silent giant remains fully loaded, operating on an internal countdown that science can track but cannot precisely date. The true baseline for what is stored beneath the Pacific Northwest is recorded in the physical wreckage of the year 1700. On the evening of January 26th of that year, the entire length of the Cascadia subduction zone released its stored energy in a singular, full-margin collapse estimated at magnitude 9.0. Because this disaster occurred prior to written historical records on the continent, its reconstruction stands as one of the most rigorous diagnostic triumphs in earth science, combining independent strands of geologic and historical evidence. The primary physical witnesses are the ghost forests. Along the tidal estuaries of Washington and Oregon, vast groves of western red cedar stand dead in saltwater marshes where they cannot naturally survive. Stratigraphic analysis shows these trees did not slowly decay. They died standing, their roots suddenly submerged in saltwater when the coastline dropped by a meter or more in a single co-seismic subsidence event. Directly overlying these drowned soils, researchers mapped distinct sheets of marine sand, the physical signature of a massive near-field tsunami that swept inland immediately after the subsidence. This American evidence provided the mechanism, but the exact timestamp was retrieved from the high-resolution historical archives of Japan. Combing through historical logs, scholars identified an orphan wave, a large tsunami that struck the Japanese coast on the morning of January 27 and 28, 1700, without any local earthquake to explain it. By calculating the trans-Pacific travel time of this tsunami and matching it to the tree ring data of the dead cedars, scientists established the definitive date and time of the Cascadia rupture. Further verification came from the deep ocean floor. Long sediment cores pulled from underwater canyons offshore revealed repeating layers of turbidites, coarse sediments shaken loose all at once and deposited by massive undersea avalanches. By dating these turbidite sequences, geologists identified 19 to 20 full-margin ruptures over the last 10,000 years, with the most recent event matching the 1700 timeline. This past event provides the precise scale for the next structural failure. A modern magnitude 9.0 rupture will subject the infrastructure of the Pacific Northwest to 3, 4, or 5 minutes of continuous, relentless ground motion, long enough to cause widespread soil liquefaction and collapse buildings designed only for shorter shocks. Simultaneously, the coast will plunge downward, and within 15 to 30 minutes, a massive tsunami will inundate the lowered terrain. This historical baseline explains why the morning's magnitude 5.5 earthquake cannot be dismissed as routine background noise. While it occurred on a separate horizontal transform boundary rather than the primary megathrust interface, it occupied the exact southern segment that has been loaded by plate motion for over 3 centuries and was actively strained by the 3,000 silent tremors earlier in the week. The 1700 event proves that the energy reservoir is fully capable of an ocean-drowning release, and the morning's minor quake was a physical reminder that the structural limits of this system are being continuously tested. The rigid data from the past strips away all comfort, demonstrating that while the timing of the next megathrust rupture remains completely unpredictable, the eventual recurrence of a full-scale structural collapse is a mathematical certainty governed by the unyielding accumulation of tectonic strain.